Hi everybody, Patrick here from EngineeringShock.com and PaintballProps.com. This is an Arduino tutorial lesson that covers hardware and software for my current Kickstarter campaign. If you haven't already checked it out, click on the link below. It is for an Arduino Shield and an Arduino prototyping board, which I'm currently working on right now. And in this video we're going to talk about the ADC pins of the Arduino. We're going to talk about variable voltage dividers using a light-dependent resistor, or LDR. It's hard to see, but it's right in there. Right now, I'm going to explain how this all works, but just to show you, right now this is low light. It's giving me a value of 678 roughly, and that value will be anywhere from 0 to 1023 depending on the light level in the room, because of the 10-bit ADC, analog to digital converter. In low light, that value goes up. Now we're at 900, and if I have a bright light over the light dependent resistor, that value goes down. In case you can't see, we're now in the 300 level. So in the next video, we're going to have some more fun with this. We're going to make a continuation of this specific circuit to do more with it. But just for this video, we're going to talk about the hardware and the software behind this little project. So follow along with me. Here are the connections. At the top of the 10k ohm resistor, connect that to the 5-volt line. The second pin of the LDR, connect that to ground. The area in the middle, the divider, connect that to A0. Now A0 has there is a via over top of it, so it looks just like a 0, right below A1. Now as for the LCD wires that we need to place are all in yellow. Pin 4 to RS, 5 to E, 6 to D4, 7 to D5, 8 to D6, and 9 to D7. Once you have those connected, all we have to do is place our LCD into its connector slots, and we're off to the races. Lastly, the B1 pin at the bottom corresponds to our button number 1, which has normally high output. Connect that to pin 2. I'll mention this only once. You might want to turn your speakers off and ignore me completely and simply read the text that I've provided here. You might find it to be a little bit easier than to both listen to me and to read what I've written down on the page. In any case, what we're going to do is we're going to make a variable voltage divider. Now, if we want to make a fixed voltage divider, we would use two fixed resistors. R1 is 10k ohms, 10,000 ohms, and it is a fixed resistor. The LDR, light-dependent resistor, is variable. It offers a variable resistance, and because it offers a variable resistance, we're going to see a variable voltage on the V+ line. If the LDR was fixed at 10k ohms, then we'd have R1 10k and LDR of 10k, which means that an equal amount of voltage would be dropped along R1 and the LDR. In this case, 2.5 volts would be dropped along R1, and 2.5 volts would be dropped along the LDR, because our V+ line is 5 volts. Our VCC line, our power supply, is 5 volts. If both resistors were equal, then half of the voltage supply would be dropped along the R1 and half would be dropped along the LDR. And so, but what if we had a variable resistor, a light-dependent resistor that changes resistance based on light? What I've done here is I've provided some formulas, some simple formulas. You just need a calculator, and you don't even really need a calculator. So, well, you probably need a calculator. Get your calculator out, read this page, go through the calculations, and I'm positive you'll get them right. But let me just say one more thing before we move on. If the LDR, the resistor connected to ground, is large, then most of the voltage is going to be dropped along that resistor, and very little of that resistance is going to be dropped along R1, which is connected to 5 volts, which means we're going to have a small voltage drop along R1, and we're going to see a relatively high voltage on the V+ line. If the LDR is a very, very small resistance in ohms, say 1,000 ohms or less, and R1 remains at 10k, then very little of the voltage is going to be dropped along the LDR, and most of the voltage will be dropped along R1. That said, we're going to have a very low voltage on the V+ line. This is how a voltage divider works. So do the calculation and we'll go on to the next page. The answer is 4.902 volts, so almost 5 volts. Of course, I'm rounding up just a little bit. Now I'm giving you some real questions, some questions that you can, using the same formula as before, reiterated at the bottom of the page. Go through these two questions, record your answers, and I'll give my answers on the next page as well, just to ensure that you understand where we're going with this. For question 2, my answer was 0.4545 volts. For question 3, my answer was 4.28 volts. I hope you're all following along with me. Now, what we're going to do is we're going to take this variable voltage coming from our voltage divider, and we're going to process it. We're going to change it into a digital representation. Now, when I say analog representation, I mean any voltage in this case from 0 to 5 volts. But we want to change that into a number. We want to process it and turn it into a number. And how we're going to do that is we're going to use our ADC, our analog to digital converter. The Arduino has a 10-bit analog to digital converter. That essentially what it will do is it'll take our variable voltage and it will break it down and turn it into a number between 0 and 1023, giving us 1024 different possibilities. And so what we're going to do is we're going to sample the V+ line on the A0 pin, and we're going to print that value to the LCD. And what we're going to do is we're basically going to put different kinds of light on the light-dependent resistor and see how this digital representation changes. So here's the formula is below. First we have to find our divisor. We take our total voltage, which is 5 volts, divided by our total bit data, 1024, giving us roughly 0.00488828. That's just a divisor. So here's how the ADC takes a sample. It takes the sample and it divides that sample. The ADC reading takes the voltage on the V+ line and divides it by the divisor. If V+ was 2.5 volts, exactly half of 5 volts, and you divide that by 0.00488828, then we get an ADC reading of 512, which is exactly half of 1024. So we get a digital representation of how much voltage is on the line. This code and all other code samples for all other videos that I make for this campaign will be included at the end of the campaign to all pledges. But if you're not a pledger, you can still take some education from this, and you can essentially retype it out if you'd like. At the top, we include our liquid crystal display library, which will allow for us to easily use our 1602 LCD. We define our button on pin 2. Now, we're not using this button for this specific project, but we will be using it on our next video. We set up an integer result, and we're setting it to a value of 0. This is essentially a register. We're going to place our ADC samples into that little integer result. And we'll do that a little bit later. We're doing in our void setup. We're going to set up our LCD, declare our button as an input, and print ADC light level on the upper line. Now, when we do LCD begin 1602, means we're doing 16 characters per line, 2 lines. And we're clearing the LCD, waiting 200 milliseconds just as a delay, 1/5 of a second. We declare our button as an input, and then by setting set cursor to 00, we're placing the cursor for our LCD on line 1 on the far left, so upper left. Then the LCD prints on the first line, ADC light level, colon. From here we go to the void loop, and these 4 lines of code will loop over and over and over again. Result equals analog read on pin 0. So whatever voltage is on A0 will be turned into a digital reading between 0 and 1023 and placed into result, our integer. Then we're going to set the cursor on the LCD to line 2 by placing set cursor to 0, 1. Then we're printing result, so we're printing the value in result. Then we wait 500 milliseconds, half a second, and go all the way back to the beginning and take another sample of the analog to digital converter. We just keep printing that result, so it'll keep updating every 500 milliseconds. So let's have a closer look. Now you should know how this all works, guys. thanks for watching. I hope you find it educational. I hope you'll check out the Kickstarter link below. And if you are a pledge already, thank you so much. Again, Bright Light, we're at 400, 300. If we had a laser, we could bring this down to under 100, I'm positive. Low light, 900. Room light, roughly 681. And you'll get different values that are different light-dependent resistors. They all work. They all have different values for the relative resistance. Some might have a low value of 10K and a high value of 1 mega. They're all different. So anyway, thanks for watching. I hope you found this video useful.